Welcome to the another video of the electric drive. In this video, our objective is to determine how to determine the equivalent drive parameter. The thing is that when we have a drive, so it's not like motor alone having some inertia J0 is there. It's like combination of some motors over there. So let us say we represent a motor like this, right? And it is connected with another a motor load or type of thing, some another load or another motor, which is again connected with one teeth, one that is called the gear ratios. So there is a gear over here, another gear is at this place. So from the size you can see that number of teeth in the small one is obviously very less, N1, and the number of teeth of the bigger one is N2. We can say also the radius of this diameter of this wheel, of this gear, small gear one, the small wheel is R1 or radius is R2. But here instead of going for R1 and R2, we can sort it out by writing like N1 and N2. Now the motor is, this one is motor and the other one is, let us say, represent the motor load, right? So the together they all combine to say that this is the load of the entire motor is nothing but J0. And the speed with which it is rotating is omega m, and motor is giving a torque called Tm, electromagnetic torque Tm. So when it is giving a torque Tm, obviously in the same direction of rotation, so the rotation is, let us say, clockwise, so this will rotate in the clockwise. Since the teeth are joined, and if this is rotating clockwise, this will also rotate but in the anti-clockwise. So the shaft which is connected with this wheel, let us say here is the load which is connected with this wheel, and this is also rotating in the anti-clockwise direction. And here this one is the load. The load is having an inertia, let us say JL, and this is rotating. It may be or may not be same as the speed of the motor. It will be lesser than the speed of the motor if the structure is like this. So omega L is, let us say, omega L is the speed of the load. Speed of the load means in the rotational speed of the load. So, and the load torque TL is obviously opposite to the direction of rotation in the clockwise direction with respect to the direction of rotation of this load omega L. Correct. So now, what are the things we can take it out of from here? We can say that if the speed is high, if N1 is small and this omega m is very high, so this small wheel will rotate very fast, and this small wheel is attached with the help of teeth with a bigger wheel. Obviously the bigger wheel will rotate very slow and omega m is slow. So if number of N2 is more, omega L is less. If N1 is small or less, then omega m is high. So we can write that omega m into N1 is equal to omega L into N2. indirectly we can get a relation N1 by N2 is equal to omega L by omega M. Let us say N1 is the primary number of teeth divided by the second number of teeth is equal to A. A is a constant. Then this we can write A is equal to N1 by N2 is equal to omega L by omega M. Now what else is how to determine the equivalent drive parameter. If J0 is the inertia of the motor over here and JL is the inertia of the load, so what is the total inertia felt to the motor? That is the question. So to answer that, we can equate the kinetic energy of the thinking that let us say having a motor with directly connected with the load, and let us say the entire thing has got some equivalent moment of inertia. So I can write that what is the kinetic energy of that equivalent moment of inertia is J equivalent, and which is rotating with the same speed of omega m. So half J omega m square is that J equivalent is that virtual inertia that represents the entire inertia referred to the motor end. Because that is why we are writing omega m square, not omega L. So refer to the motor end, which is equal to total inertia of the motor referred to motor end, or total inertia of the motor, let us say. So that is nothing but half J0 omega m square. Total inertia of this load. What is the total inertia of the load? Half JL omega L square. So this is the total inertia of the load. Anything else left? No. So we can just cut this half and take this omega m downward. So what we can write? J equivalent is equal to J0 omega m square cancel plus JL omega L by omega m whole square. That term is nothing but A. We can write this as J0 plus JL A square. In this way we can get what is the J equivalent, inertia equivalent of this entire inertia. So once I know the J equivalent, we can have a single motor with J equivalent, and then we can just calculate what is the kinetic energy of that motor at any time. Kinetic energy of the entire setup, we can also find the J equivalent by using retardation test. That means run the motor first a little bit higher than the rated speed and then turn it off, then see in what is the rate at which there is a decrease in the speed of the motor. Anyway, the kinetic energy, we can, with the help of kinetic energy equilibrium, we can find like this. Another is that about like potential energy, so, or equating the power at both the ends. So if I equate the power at both the ends, so power formula will be T times of omega. So what is the equivalent torque? So we can write what is the equivalent torque, let us say T equivalent refer to the motor end, and omega m is the speed of the motor. Correct. So T equivalent into omega m is equal to what is this motor load. So motor is also load, it has got a load torque. So let us say TL0 is the load of the motor. So I can write here TL0 is the torque of the motor because of its because it's inertia or something, because it has got a load, it is representing a motor its own load. So TL0 is the torque, and multiply with omega m. Another torque is here TL, multiply with omega L. So here we can easily find the equivalent torque. Refer to the motor end is equal to TL0 plus TL omega L by omega m, and that is equal to TL0 plus TL into A. So we get the equivalent torque and equivalent inertia. So far we have considered that, let us say it is a rotational motion only, and one shaft is connected to the motor load or shaft is connected through a gear to the another load. This picture can be represented in the book like this, that is this one, and connected with this one, connected with a gearbox. The gearbox can be represented like this, and this is connected with the load, and the gearbox having a turn ratio A is given, and here you can have TL as load torque, TL0 as motor load torque, and Tm is the electromagnetic torque. Right, so these are the different way of picturization of this schematic diagram for the question. Another thing is that this gear may not be like 100% efficient. How do you know that this gear is 100% efficient? Maybe the efficiency is less, like 100% means the wheel is coupling is very good and it is giving out a very 100% efficient out of it. So whatever the speed this is running, the same speed with the ratio it is other side is running, it's fine. But we cannot guarantee like 100% efficient. Mechanically there is some gap, so the efficiency has been given in terms of eta. Eta is obviously less than 1, less than equal to 1. So if this efficiency will come into picture, it will not check out for this inertia but for the power, deriving the equation for power. So let me write down this equation for power. So T into omega m equivalent torque is fine. You have got a motor load, that is also fine. You have got a load which is after this gearbox will have an effect that this load will be reflected on the motor end with the division of efficiency here. So when we divide the efficiency, that means the value less than 1, so obviously this entire value will rise up. So if the efficiency is less than 100%, so the load torque reflected in the motor end will obviously be higher. So that's why here you will get the efficiency term eta over here, and this here you will get a efficiency term eta. So like that this equation gets changed if the efficiency is not 100%.